Hi there guys, well, welcome back. We're now working on the exercise 4H. And for those people who have seen differentiation before, not necessarily the proofs and differentiation by first principles, but what they're calling here the power rule for differentiation. If you've seen that before, then this exercise is going to be really straightforward. In fact, you can just have a go at these questions straight away and you might think, well, I don't need to bother listening to this video. And maybe that's true. However, there's a couple of proofs at the start here, and hopefully we can do these a little quicker than we did the proof from last time, which was proving that differentiability implied continuity, but not necessarily the other way around. Okay, so it starts off by actually proving, and I'm not going to overdo this one. It's proving that if you've got the derivative of two functions which are adding together, fine, here we go, proving that the derivative of a sum or difference of functions. Okay, so it's just doing a general proof to say that, look, if we add together two functions, then when we differentiate that, that's the same as differentiating them separately and then adding them together as well. Now, why that's important is because, again, when we look down at the exercise, you'll see questions saying y equals 3x to the 5 minus 4x squared. And how do we know that we can then just use the power rule on each of those separate terms within our function? Well, the reason why we know that is because we've made this proof at the start of the chapter. Now, I'm really not going to overdo this one, but I'm just going to talk it through just really briefly, okay? And then I'm going to try and prove the power rule, which is the investigation that they're dealing with here as well. So let's just have a look at this. So they're not actually using a particular function here. They're just saying, look, if f of x is comprised of the sum of u of x plus v of x, and likewise it could be minus v of x there, or there could be a negative in this function. So it's sum and difference, of course. So when we're working out f dash of x, that's the same as saying, well, let's put in x plus h into this function here. Then let's put x into this function here, and let's divide by h. Now, you can split up those fractions to combine. So split them up into fractions by, saying this and this and this and minus this. And then we can combine them again to put the u's together. Or in other words, we can just multiply this out and put the u's together and put the v's together. Okay. So putting the u's together, we get this. Putting the v's together, we can get this. Now, using the properties of limits, we can split these two things up. So we can split it up into these two parts, and now we realize that we've got the derivative of u and the derivative of v. That is what enables us to differentiate particular terms according to the power rule or according to whatever rules of differentiation that you have later on for each of those terms. Okay, so that's important, but it's pretty easy as well. There's nothing too difficult there, so that's why I'm not over talking that one. Okay, now there's the little formula. There's the box which they give you there. If f of x equals ux plus vx plus minus, then the derivative is equal to those two things, differentiated with plus minus as well. Okay, and there's another one here, just an extension to that. It's just saying, well, look, if we have a linear multiple of a differentiable function, likewise, we can take out the c in that case as well. So, if we know how to differentiate x to the power of 5, this little addition here is just saying, well, therefore we can differentiate x to the power of 5 and then times that by c as well. That's what they're coming up with here. It's just a little extension there. I'm not going to go into that. Okay, now this is what we care about here. Okay, so this is the rule that some people have known for quite a while. We're finally there in the book. So that's saying, the rule is saying that if we take, for example, x to the power of 5, then to differentiate it, we bring the 5 to the front and we reduce the power by 1. That's all this is saying here. X to the 5 bring the 5 to the front, reduce the power by 1. And this is going to be f dash of x, and this is how we get from f of x to this thing over here. Now, obviously, not all functions look like this. So this is just a particular rule for polynomials, or in fact, for negative or rational powers as well. So it says that n is a positive integer here, but this is also working for negatives and rational powers as well. Well, we're going to prove this in particular. I know it says that n is positive integer there, but we're going to prove it for positive integers here by considering the binomial expansion for positive integers. But likewise, you could do this for negative and rational powers by using the alternative binomial theorems or binomial expansions for negative or rational powers. Okay, so what am I talking about? I'm saying that we can use f dash of x is equal to the limit of h tending to 0 of x plus h there to the power of n minus x to the power of n divided by rh. Now we can expand this using the binomial expansion. Might need a little bit more space here. Limit. Limit. I meant to say limit. Okay. So, right, the limit of, and then we've got x to the n, expanding this thing here, plus nc1 times hx to the n minus 1 plus nc2 h squared n x n to the minus 2 plus all the way down to that last term, which is going to be h to the power of n. That's the expansion there, and then we're taking away x to the power of n, and we're dividing the entire thing by h. Put brackets around there and there if you want to. Okay. Now we can see that x to the n is cancelling with this, just like with a lot of your differentiation from first principles. If you did x squared and x cubed, then you'll know that this and this are going to cancel. Okay, so if that cancels, then we're left with n c1. I'm going to actually factorize out an h here from these terms, essentially. We've got h n c1 x to the power of n minus 1 plus h, because there's h squared there, so it's h times h is h squared, and then we're getting nc2 x to the power of n minus 2 plus dot dot dot. We're going to take the h out of this, and the last term, which we really don't care about that much, is h to the n minus 1, and of course this cancels with this, so that's gone, and now we can divide by that h. And then we've got the limit as h tends to 0 of this thing here. Okay, well, you can see that as h tends to 0, all of these terms are going to become 0 because we've got 0 times something. And so we're getting nc1. Now, nc1 is just n, of course. We're getting nc1 x to the n minus 1, and then we're done. Okay, so there's n x to the n minus 1. So, in fact, the proof of this rule here is actually pretty straightforward because you just need to use binomial expansion with x plus h to the power of n. Okay, so that's done. So now we know that for any term that we have, say we have x to the power of 6, or at least any term with positive integers, then we can times by the power and reduce the power by 1. Done. Okay, now as I said, this extends to negative powers and rational powers by using the different versions of the binomial theorem, but I'm not going to go there now. If you want to have a go at that, you are welcome to, of course. Okay, so in the book, they lead you through this in investigation 12. Again, I'm not going to do that now. And then we've got here example 16. Okay, so let's do these then. Example 16, differentiate this with respect to x. Well, for most of you now, it's going to be pretty easy. So we've got dy dx, or f dash of x, is equal to times by 4, give us 2, and reduce the power by 1. times by 3 and reduce the power by 1. Times by here the 2, which is 6, and reduce the power by 1. Now x to the 1 has a power of x to the 1, so we're going to times by 1, it gives us minus 1. We can get x to the power of 0 there, which is still 1. We're left with just the minus 1 there. Now here we sort of have an x to the power of 0 times by 0, and you're going to end up with a plus 0 on the end. Now this last part is just worth thinking about. When we have minus x plus 3, if that was our function, then we'd say, well, the gradient is clearly minus 1, because look, in the form of y equals mx plus c, where m is the gradient. Okay, so for that last part, you don't need to overthink it. You just think, well, it's a linear function, and the gradient is in front of x. Okay, so there's the first one. That's example 16. That's done. When it says with respect to x, I think I've said this before, sometimes you might see that written as WRT, x, with respect to x, because it's used quite a lot. And yeah, and that's essentially saying differentiate with respect to x. That's what it's saying here, ddx. In fact, later on you can start saying ddx of something or other. Say, for example, of x to the power 4 gives us 4x cubed. ddx can be used as an operator. And what we've done there is we've put in for our function x to the power of 4 for y, for example. Okay, so let's look at the next one. So we've got example 17, then example 18, and then we are done. Quick one, this. So example 17. So we've got this function here. We can see that this is just a fraction, which we can divide by x squared. So this one says 2x to the 5, and there's x squared on the bottom there, plus 3x cubed, and there's x squared on the bottom there, minus 1 over x squared. There we go. This is just f of x. We haven't done anything to this at the moment. We're just playing around with the function. So we're getting 2x cubed plus 3x minus, let's put it in its index form, x to the power of minus 2. So now f dash of x is equal to 6x squared times by the 3, reducing the power by 1, plus 3, that's just like mx, and then plus 2x to the power of minus 3. And we're done there, but perhaps we should be consistent with the question, because the question is not using sort of index form here, it's using a fractional form. So let's just say 6x squared plus 3 plus 2x to the power over x to the power of 3. Obviously, the minus 3 is only applying on the x, not on the 2, so the 2 remains on the top. Okay, so there's that one. That's example 17. And for example 18, let's check this one out. Sorry, there we go. And, it's playing up. It is struggling. I'm doing things too fast. We're doing these questions too fast here. Example 18, find the equation of the normal to this curve. Well, let's find the gradient of this curve now. So we've got f dash of x is equal to, well, the minus 1 is just a constant. Constants just move the same function up and down, so it doesn't change the gradient at any particular x point. It just moves the whole thing up or down. So the constant is just, it's not going to have any effect. This one is going to be minus 1, and then we've got minus 10x to the power of 4. So times by the 5 and reduce the power by 1. So now substitute in 0. So we've got f dash of 0 minus 1 minus 10, 0 to the power of 4. You get minus 1, of course. Now the equation of the normal is, remember, the gradient of the normal is 1 minus 1 over m to the power of t. The gradient of t, and the gradient of t is this. So we're getting minus 1 divided by minus 1, which is plus 1. Now we've got y equals mx plus c, so we've got 1x plus c. We just need c. And in order to find c, we'll need a coordinate point. So we need the coordinate point at x is equal to 0. So we need f of 0. And f of 0, you can see all of this is going to disappear, and we're just going to get minus 1. Okay, so in other words, when we put in 0, we get -1, and that, although we can put in 0 here and -1 here, we're really overthinking things, because this actually tells us the y-axis intercept. This is the y-axis intercept. So we've got 1x, or just x, minus 1. So there, our equation of the normal. Okay, well, that's a pretty quick video there. That's done. We've got 4H. 4H should be some fairly quick practice using these rules. And next time round, what have we got? We've got the product rule. At least it's, sorry, not the product rule, we've got the chain rule. In fact, the next one is about the chain rule. Okay, so there's different rules for differentiation, and the next one is going to be saying, well, what if we have a function of a function? That's where we're going. Okay, well, good luck with 4H, and hopefully see you for the next video next time around.